Okay, so today's lesson 5.2, the focus is on solving exponential equations. And in general, in math, when we say solving, it means finding an unknown, okay? So finding what the value of x is or y is or whatever it is. You're trying to find the unknown variable, right? So an exponential equation has the unknown in the exponent, all right? So when we are solving exponential problems, as I just said, you're solving for the unknown, whatever the variable is. And in these cases, that unknown will be up top in the exponent. All right, so how would you do this? Well, in this problem right here, you notice that we have the same base. This is 3, and this is 3. So what value of x would make it so that left side is equal to right side? Well, in this case, because they have the same bases, you just equate the exponents. So I can just look and I can say, well, because they have the same base, I just make the exponents equal to each other. So in this case, x is equal to 5. So if the same base, equate exponents. Okay. What about B? Well, in A, we had the same base. But in B, well, we don't have the same base now. And this clearly I have a 9 and I have a 3. But we need the same base, all right? We need to find a way to make the same base. So you need the same base. So similar to what we did in 5.1 lesson, let's manipulate that 9 so that we have the same base of 3. We can think of 9 as the same thing as 3 squared. So this 9 right here, that becomes 3 squared. Still put to the power of x, okay? So that x doesn't go anywhere. And then on the right-hand side, you still have 5x minus 6. All right, well, let's first we have this bracket here. Let's get rid of that bracket, all right? So we have an exponent of 2 being put to an exponent of x. So we now have 3. We have to use our multiplication, or power to our power. So that's 3, 2x. And then on the right side, you still have 5x minus 6. So now we have the same base. So equate exponents. So same base, equate exponents. So now I can take that 2x and set it equal to 5x, because in order for these same bases to be equal to each other, they have to be put to the same power. It's like 3 squared has to equal 3 squared. It's not like I can have 3 to the 4 or something, right? Like these need to be equal to each other. That's what this equal sign means. So I have to equate exponents. So 2x equals 5x minus 6. Well, now it's just solving a linear problem. So we have to bring the unknown to one side and everything else to the other. So we have 2x minus 5x, and that would be equal to what's left over on the right, negative 6. So we have minus 3x equaling negative 6, or x would have to be 2. And there we go. So no, when powers have the same base, we can equate, as I said twice now, the exponents. Solve for x, right? So now we can see, similar to what we did before, we have an exponent, the unknown x in the exponent. But what do we do here? What is this? What do we do on the right-hand side? This is a 27 over here. Well, in order for us to solve this problem, we need to have a way of equating the exponents, okay? We have to somehow turn this 27 into the same base of 3. right? Why you're equating the exponents is because the unknown is in the exponent. That's how we have to set up this problem, right? When you're solving for the unknown in the exponent, you gotta have to make equivalent bases. So turn that 27 into a base of 3 in order to do this. So 27, well, that is the same thing as saying 3 to the power of 3. So we rewrite the left, which is 3, 2x minus 5. And on the right-hand side, you can now have that as written 3 to the 3. There's no difference between 3 to the power of 3 or 27. We now have the same base. So that tells us we can then take our exponents, 2x minus 5 on the left, and set it equal to each other, 3 on the right. Take everything that's common to one, leave the variable on one side and bring everything else to the other. So 2x, 3 plus 5, 2x is 8, or x is 4. B, 16 to the power of 1 minus 2x equals 8 to the power of 1 minus 3x. So we need same bases because the unknown is in the exponent. We need to set up this problem that in a way that we can set the exponents equal to each other to solve it. So in order to set the exponents equal to each other, it's like working backwards, you need to have same bases. So rewrite these bases. So 16, all right, pause for a second. How can we rewrite 16 and 8 to be same? Well, go back to the lowest factor, okay? So always try and think of like, what is my lowest like base exponent that of 16 and 8? Well, 2, all right? And in practice that comes. So 16 can be rewritten as 2 to the 4, all right? And it's still being put to this exponent here. So still being put to the exponent 1 minus 2x. And then on the right-hand side, 8 can be rewritten as 2 to the 3. And that's being put to the exponent 1 minus 3x still. Well, you have an exponent put to an exponent. So that tells us we multiply, okay? That happens on both the right and the left there. So left and right. So on the left-hand side, we have 2, our base. Well, we multiply this 4, and careful, you have a binomial here up top, so that 4 has to get multiplied to both the 1 and the 2. So that becomes 2, 4, actually, I'll write it in the same color, 4 minus 8x. Same thing on the right-hand side. This 3 has to go to both that 1 and that minus 3. So that'd be 2, 3 minus 9x, right? You're multiplying. Now you have same bases, so you set the exponents equal to each other. So this is 4 minus 8x equal 3 minus 9x. Bring the variable to one side, bring everything else to the other. So we have 4 minus 3 is negative 9x plus 8x. That's 1 equaling negative x, or x, I'm just going to write the x on the one side, is equal to negative 1. All right. C, 5 to the power of 3x minus 4 plus 3 equals 4. All right. Well, in the previous problems to this might look more challenging. In the previous problem, notice how we had only one term on both sides. This is a single term. This was a single term. Well, I am giving you 2 terms now on one side. 2 terms. Problem is 3 and 5 are not similar bases. So how can we deal with this? All right. And again, pause at any point. Try out this problem for yourself. Your goal is to solve, okay, this whole lesson is about solving this exponent up top here. So you have to have a way to equate bases to be able to get that exponent up top to be the same. Or so the bases to be the same to solve for the exponent up top. All right, well, with practice, you'll see, okay, I'm gonna bring this 3 over here. Because what will happen then is I'll have 5, 3x minus 4 is 4 minus 3. And on the right-hand side, that will simplify down to having 1 there. And when anything had, another way to think about what base to what exponent would give you a value of 1? Like where does 1 come into play when we're dealing with exponents? Well, we learned in the first lesson, any base put to the power of 0 will give you a solution 1. Any base is the key thing here. So in my case, this could be 5 to the 0, and that would give me a value of 1. So now on the left and the right, we have a base 5. All right, and that allows us to equate our exponents. So now we have 3x minus 4 equaling 0. That's 3x equaling 4, or x is 4 thirds. Okay, this whole concept of having a 1 on one side comes up a lot, okay? So start this question. You'll see this concept of having, like, using this relationship, going from here to here. It happens quite a lot. Okay, D. 10 to the power of x plus 4 is equal to the square root of 0.001. Well, this is a base 10. This right here, this 0.001, that's the same thing as me saying square root of 1 being divided by 1,000, because you're in the thousandths decimal place. So same thing as the previous problems, we need a way of having the same base to be able to solve the exponent x up top. So we need the same base. So we need a 10 here, and we need a 10 over on this side as well. All right, or whatever the lowest common base is. But I know 1,000 is a base of 10. That is the same thing as me saying, under the square root, well, 1 over 1,000 is the same thing as me saying 10 to the power of -3. All right, you know what? I'll do one last step. So that's the same thing as me saying 1 over 10 to the 3. All right, so on the left side, we still have 10x plus 4. So 10x plus 4. Well, 1 over 10 to the 3, that's the same as 10 to the -3. Well, this square root, let's get rid of that. Well, a square root is the same thing as me saying, what is my base under the root? In that case, it's 10 minus 3. That's what's under the root. And a square root is me putting an exponent of half. Okay, so on the right-hand side, we now have an exponent put to an exponent. So you have -3 being put to the power of half, so multiply them. That is the same thing as me saying 10 to the -3 over 2. Now we have the same base. Okay, that was our goal. And we can set the exponents equal to each other. That's x plus 4 is -3 over 2. So then x is equal to -3 halves minus 4. So then x is equal to, well, if you get a common denominator, right, -3 over 2 minus 8 over 2, that'd be the same thing as -11 over 2. Okay, E. So 2 to the power of x equaling 5. So you might, like, as we approach the problems, you might be thinking, how can I equate these bases so I can set the exponents equal to each other? In all the other problems, the bases were factors of each other, all right? 10, 2, 3, okay? But 2 and 5 are prime numbers. They're not factors of each other. There is no way to turn either one of those into a base of each other. So there is actually no way that you know how to solve this problem. There is no way to turn 5 into some sort of base of 2, like 3.2 or something. It just doesn't work out nicely. And in order to solve this, this is where this unit is going. We are going to learn something called logarithms, okay? So you need to learn, or need to use, logs. So that's eventually where we're getting to, okay? How to solve exponential problems where you can't equate the bases. So that's how you would solve E. Okay. Question 2. I'm just going to zoom out for a second. All right, so we have, well, question 3 is similar to 2. But in question 2, we have similar to the previous problem, right? Where you're solving these exponents, these unknowns in the exponents up here. But the difference between these ones here versus what you did before is notice that we have two terms that have the unknowns, right? 2 terms, here and here, right? And even 3, same thing, here and here. So the approach to these problems is different than what we've done in these previous ones, okay? Because look at the previous ones. Every other single one, the unknown is just one term, right? And is kind of like a one step. So these ones require a little more work, right? A little more challenging. So because we have 2 terms here, well, we have to find a way first to get them to have a similar base. We want to have these exponents here have a similar base, right? So we can see they look quite similar, but not entirely the same, right? Like in the first one, we have 2 to the 2x, and then that second one is just 2x. Well, this right here, this 2 to the 2x, that is the same thing as me saying 2 multiplying x, right? Well, when do you see a multiplication of exponents? That comes from using our rule mn, which happens when b is being put to the m and being put to the power of n. So you are given 2 to the 2x. What you need to see is that's the same thing as me saying 2 to the x to the power of 2. All right? And in doing that, that allows me to rewrite this base. I'm not going to put a double equal sign. That allows me to rewrite this as 2 to the x to the 2, because now I have this and this one being the same. All right, that's step 1. When you've identified that, hey, this is like 2 terms having an unknown. That's the first thing you want to do. Is you were trying to get those unknowns to be the same. Same base. So 2 to the x plus 32. Okay. Well, we have a trinomial. Like this is a trinomial. You have 3 terms, right? Where 2 of our 3 have an unknown in it. This looks awfully similar to something we've seen before, where you have 3 terms where 2 of them have the unknown. A quadratic. So when we solve a quadratic, remember we are getting factors, right? Like x plus whatever, r, and like x plus, I don't know, like s or something, right? And your solutions to these factors, when x is negative r or when x is negative s, those are the solutions that result in your quadratic equaling 0. So we're going to be using that principle, okay? So you might not see it looking like a quadratic yet, but let's say I say let a equal 2x. Well, wherever I see a 2x, I'm going to put an a. So this 2x, that becomes a squared. Minus 12, and then this 2x, that becomes just a. Plus 32 equaling 0. So now it looks like a quadratic. So we are going to factor this to solve this quadratic we've created. So we need 2 numbers that multiply to 32 and add a negative 12. So if we factor this, this would be a minus 4 and a minus 8. So you have two factors that could possibly give you a solution as 0. So you have one scenario where a minus 4 equals 0. So a equaling 4. Or you have the other scenario where a minus 8 equals 0. Or a is 8. But I'm not solving a. A is not the question. I have to solve for x. So we have to sub back in. So sub a for 2x again. Or 2x for a, vice versa. So we have 2x equaling 4. And we have 2x equaling 8. Well, now this looks like what we've done in the previous problem, in question 1, where you just have a single term with an unknown equal. So just make the bases equal to each other. So on the left-hand side, 2x equals, well, 4 can be written as 2 to the 2. So equate exponents, x equaling 2. That is one solution. 2 to the x equaling, well, a can be written as 2 to the 3. So equate your exponents. So x could equal 3. That is a second solution. So big picture, what did you just find? You found that if you substitute either a 2 or a 3 into those x's right there and, follow your BEDMAS and you solve this, it will equal 0, okay? So you solved the unknown x. That would turn that equation into 0. And there's two solutions, x equaling 2 or x equals 3. Let's try it again for b. All right, very similar. The only difference is we have this binomial, right? This addition happening in the exponent up top here. So where do you see additions in exponents? So if I have some base, right, our base being 3, and there is an exponent where there's an addition, well, that comes from taking b to the m, multiplying b to the n. When you have two things multiplying, you add exponents. So this right here comes from saying 3 to the 2x multiplying 3 to the 1. And let's just rewrite the other ones. And same time, I'm going to bring this minus 3 over. So that becomes plus 3 because I want to set this equal to 0. Okay, so it's still not quite similar. I'm going to rearrange this first one here. I'm just going to say I'm going to put that 3 in front. All right, so that's this, and 3 to the 1 is just 3. So it's 3 to 3, 2x, minus 10, 3x, plus 3, equaling 0. Well, now we have to do the same thing that we did in the previous problem, right? This is 3 to the 2 multiplying x. So I can rewrite that as 3, oh, it's really big, 3x squared, using the same thing we just did above, minus 10, 3x plus 3 equals 0. Okay. Notice again, you have your two terms that have the unknown. So first term, second term, right? And if we let a, once again, be equal to the thing that has the unknown, so the base with the exponent, the power, so you're letting it equal the power with the unknown, so this right here. So let a equal 3x. Well, you're going to see that you're going to have 3 multiplying. Well, this becomes a squared. So it's 3a squared minus 10, that 3 becomes a plus 3 equaling 0. Okay. And again, in the effort to get you to practice your factoring, pause the video, try and factor this on your own. All right, we do want to get faster at our factoring, so a little bit of guessing and checking. All right, we can't always use decomposition. All right, so in your head, or if you do need to do decomposition, please do it. But you'll factor this, and you'll find that this is 3a minus 1, a minus 3, and that's what gives you 0. So we have two possible solutions. We have the solution where 3a minus 1 equals 0, or we have the solution where a minus 3 equals 0. So a could either be 1/3 or a could be 3. But just as we did before, we don't care about a. I want to know what x is. So we have to sub back in. So sub back in a, and so 3x for a. So we have 3x equaling 1/3. And we have 3x equaling 3. Okay. So on the right-hand side is a little easier to see. When you have just a base and you don't see an exponent up top, technically there's a 1 there. So this would just be, once you equate the exponents, x equaling 1. But on the right-hand side, or sorry, on the left-hand side, they're not like you can see there's clearly a 3, right? But they're not the same. One's a fraction. Oh, jeez. Okay. Well, this fraction right here, that's the same thing as me saying 3 to the negative 1. Right? Because I can just reciprocate my fraction. So then, now we can equate, we have same bases, we can equate the exponents. So x equaling negative 1. There's your second solution. Okay, so challenge yourself, right? If you want to pause the video, try doing this question, all right? So I'm going to start. It's a good question. So just as we approached it before, let's try and get these bases right here, these powers, to be the same. So we can clearly see that one of them has a negative, right? This 2 to the negative x, well, that's the same thing as me saying 2 to the negative 1 multiplying x. So what happens when you have multiplying exponents? Well, that's the same thing as me saying 2 to the x to the negative 1. So if I rewrite that, that's 2x plus 4. Well, that's now 2x to the negative 1. All right, equals 5. So let's substitute. So let's let a equal 2x, just because it makes it a little easier to look at, and you might see where we can go then. So a plus, I'm writing in purple, so a plus 4a to the negative 1 equaling 5. Well, a to the negative 1, that's the same thing as me saying a plus 4 over a equaling 5. Well, how do I get rid of this fraction here? Well, in order to get rid of the denominator, what I want to do is I want to multiply this by a, right? Ultimately, I want to multiply this term right here by a, because I will get rid of the denominator, because we don't like things on the bottom. But I can't just multiply this by a. I have to multiply everything, left side and right side, by a. So that means this a will go to here, and I'll get a squared plus, well, now that a will go to this 4, and it will cancel out. So that's why you get plus 4, and we succeeded. We got rid of the denominator. And on the right-hand side, we have 5a. So we now have a quadratic. Let's bring this 5 to the one side. So that's a squared minus 5a plus 4 equaling 0. And solve it like we did before, so factor it. So that's going to be a minus 4, a minus 1 equaling 0. So you have one scenario where a could be 4, or you have the other scenario where a could be 1. But we don't care what a is. We want to know what is x. So we have to sub back in. So sub a for 2, what was it, 2x? Yeah, 2x. So that's going to make this 2x equaling 4, or get the same bases. It's 2 to the 2, x is 2. That's one solution. And then on the right other side, you have 2 to the 2 equaling 1. Well, what gives you, 2 to the x equaling 1? Well, what gives you 1? That's any base to being 0 is 1. So that would be the same as me saying 2x equaling 2 to the 0, or x is equal to 0. That is another solution. And that's it for today. All right, I'll see you in class.